안녕하세요. 저는 서울과학기술대학교 데이터셋과 석사과정 재학 중인 하산프로라고 합니다. 제가 발표할 논문은 DyG-Mamba Continuous State Space Modeling on Dynamic Graph이라는 논문을 발표하겠습니다. 이 논문은 NeurIPS 2025년에 발표되었습니다. 발표를 연구로 진행하겠습니다. I will follow this agenda for the presentation. Starting with the introductions and why dynamic graphs are hard. That's because the model must understand time, long history, and noisy interactions at the same time. Dynamic graphs are a sequence of timestamps interactions, not just static snapshots. As you can see in the below diagrams, which is edges between the nodes at different timestamps over time. Secondly, important patterns may appear far apart in time, so long-term memory matters. And lastly, real-world interactions streams contain noise, irrelevant edges, and irregular gaps. So the main pain points for the dynamic graphs or temporal graph is a long-range dependency, irregular time spans, and the input data noise. Next, we will discuss about the existing solutions for dynamic graph learnings and what are the limitations of the existing approaches. Why existing approaches are not enough? There are mainly three different types of graph learning, which are based on RNN-based, transformer-based, MLP, or JNN-based. The RNN-based approaches are good in memory, but they are suffering from vanishing or exploding gradient on long sequences. Transformer-based are handling long range lengths, but because of quadratic cost, they are become expensive on long inputs. The GNN based often efficient, but long-term memory temporalization is very limited. The main limitation for RNN based and GNN based is the weak long-term memory, but for transformers, cost grows very quickly as the input sequence length grows. The goal is that we need a method that is efficient like sequence models like RNNs, but still preserve long history and filter noisy events. So to overcome the limitations of existing solutions, the author of the DyG-Mamba proposed a new method based on the continuous state space modeling, which is based on the selective state space modeling, or S4, which also known as Mamba architectures. So they are using a continuous state space model whose forgetting behavior depends on time gap between the events. As you can see here in the model architecture, there are four main layers: the input layer, and then embedding layer, which encode the input graph, and the DyG-Mamba layer, which is a continuous SSMM layer, and then the decoder layer or output layer, which will explain each of the layers in the next slides. How this model input is represented. The model builds a history sequence of each node and combines several types of encodings. As you can see here in the diagram, first they fetch the historical neighbor of the target. For example, target node here is U, and it fetch the interactions of the target nodes to create the co-neighbor encoding, and then combine this encoding with the raw features of node encoding, edge encoding, as well as the temporal encoding. Once they create the embeddings, they will pass to the next layer, which is the DyG-Mamba main layer, which we'll discuss about it in the next slides. Now moving with the DyG-Mamba actual layer, the main innovation of this approach is first the time-aware forgetting, which inspired from the how human brain is forgetting information, which is first it forget fast and then over time it forgets slowly. And the second innovation is selective review. So it uses a selective review method that is data independent. So for the forgetting, time-aware forgetting, the rule is that lower time gaps should cause stronger forgetting. A long-time gap decay holds information more aggressively using this data-dependent approach, and a short-time gap allows the model to keep more information of the previous state. So this acting as a fast then slow forgetting patterns similar to the Ebbinghaus forgetting curve. The second innovations, as we discussed earlier, as the selective review makes the model more robust. The model does not just learn to forget, but it also learn what should review, and that's input dependence using the parameter B and C of the continuous state space modeling equation. Parameters are made input dependent, so the model will focus on usual historical signals, as we can see here in the right diagram, which the model is selectively focusing on the previous interactions of the node that is dependent of the actual input data. As a result, this selective review process significantly reduced the influence of noise interaction, so this can act as a filter to filter noisy inputs. Now that we have discussed the system architecture and we saw how the DyG-Mamba is handling time and data input dependent forgetting strategy, so how DyG-Mamba is used for downstream tasks. The same sequence encoder supports both the typical graph downstream task link predictions and node classification. The dynamic link predictions encode the source and destination histories separately, then combine them with an MLP to predict whether there will be an existing edge between two nodes or not. As you can see here in the below diagram, having the source node and destination node, we will predict at a specific timestamp will there exist an edge between them or not. And for the dynamic node classification, use one node history encode and remove the co-occurrence encodings, then classify the node state at the target time. So basically we are predicting the node time at a specific timestamp in the future, or just clustering the target node. For the experiments, they used almost 12 standard dynamic graph benchmarks using the standard DyG-Lib, which is a dynamic graph representation learning framework, and the datasets are across different domains, from social networks to financial systems, and the task they are assessed is dynamic link prediction and dynamic node classifications. The evaluation metrics are average precision and area under curve, which is evaluated based on both introspective and inductive evaluations. And the baselines they are compared against is the variety of other models, from RNN-based, transformer-based, and vanilla GNN-based. And some of them are TGN, TGAT, Graph Mixer, DyG-Farmer, and other models. As the result shows here, based on 3 different negative sampling approach, random, historical, and inductive. As you can see here in the table, this proposed DyG-Mamba outperforms almost all of the models in the random negative samplings, and in the historical negative samplings it has comparable results in most of the datasets, as well as in the inductive negative sampling. It also outperforms almost in half of the datasets the existing models. Based on the results we saw in the previous slide, the main strength of this approach is that it provides effectiveness and efficiency at the same times, and it overcomes the transformers bottleneck, as you can see here in the right side diagram. which compare two datasets, last FM and Canadian Parliament datasets, on 4 types of models: TGN, Graph Mixer, DyG-Farmer, and DyG-Mamba, which we can see that Transformer struggles with long inputs, but DyG-Mamba maintains sequence model efficiency. Here we can see that as the length of the sequence increase, DyG-Mamba performance maintains its high performance, but Transformer, as the sequence increase, it will decrease the performance, as well as it's more resource friendly, as we can see here in the diagram, the blue diagram. Both the DyG-Farmer and the DyG-Mamba speed, as we can see here, it's almost 9 times faster and 77.2% less memory consumption during the training. So now with the ablation studies, we will discuss which components is effective on the least consumptions of memory and faster training time. Each proposed part contributes, for example, time awareness, selective review, and data-dependent parameters all matters based on the result from on 3 datasets. We can see that removing the timestamp signals hurt the performance the most. Removing absolute time encoding also causes a noticeable drop in accuracy, and time awareness is critical for dynamic graphs state space modeling. And this proves that the data-dependent parameters are successfully acting as a filter for messy real-world interactions. As a final takeaway, DyG-Mamba is a continuous time dynamic graph model that is both highly efficient and robust, based on the results from the ablation studies as well as the experimental result, that outperforms most of the baseline models, as well as consuming less memory and faster training time. The secret behind that is it relies on time span over continuous state space model to preserve longer temporal information while selectively suppressing noise. The strength of this model is that it excels at long-term modeling, regular timestamp support, and scaling smoothly. The future directions could be expanding to broader interaction types, testing on larger dataset, as well as applying to other domains. And that's all. Thank you for your attention.